I might have gone too quickly on that. Are we good?
Should I go?
Go ahead. Yeah.
Let's welcome in.
Hello everyone, thanks for the introduction. So I'm Minnie from TZ Watson. This is a work that joint work with my colleague Michael. So today I'm going to talk about how I actually perform true elasticity, how the workloads can actually benefit from the auto-scaling capabilities of Spark. So as we all know that the auto-scaling, it helps detect the changes of resources. So that's how you want to do the auto-scaling. It actually helps you to reduce the cost while you can minimize the maintain the SLAs. So and current auto-scaling approaches, they they sometimes react slowly and they can often misses the opportunities that to do the optimizations. And we wanted to leverage the Yarn and Mesos framework that can help you to do the initial auto-scaling, but how the questions arise when how the workloads can actually benefit from those auto-scaling capabilities. So particularly in this study, we wanted to analyze how the scalings, how workloads can actually benefit this, from the auto-scaling. Do you just simply adding new resources, is this sufficient for this performance improvement? Does it do it proportionally to the resources that you have added? We also wanted to identify what's the current Spark auto-scaling mechanisms. Are there opportunities that we can improve? So here is the agenda. We have introduced the introduction. You know what's the problems we are targeting, and we will study the impacts of the capabilities on the different types of workloads. Then we will study what's the optimizations that we do for the auto-scaling. And I will conclude with the lessons and the future work. For our experiments, we use a 10-node virtual machine cluster. So for our baselines, we use 6 nodes. We run the workloads initially on 6 nodes, and then we perform scale up. And for the case of scale down, we initially run the workloads on 10 nodes and scale down to 6 nodes. And for each node, we had 4 CPUs, 8 gig memories, and 2 100 gig hard disks. For Yarn executors, we run configure the executors for 3 gigabytes of memory and 1 CPUs. And for Mesos, we use the maximum amount that we can have in the cluster. And we use 4 workloads from Spark Bench, K-means, PageRank, SQL queries, which runs 5 SQL queries sequentially, and logistic regression. So for how do we do the scaling? So we run the scaling experiments on both on Yarn and Mesos, but for this talk, I'm going to mainly present the results from Yarn. We see similar results on Yarn and Mesos. So for scale up, we kind of adding the new nodes by running the node managers or Mesos slave daemons. We already provisioned the virtual machines. We just run them, and then we can add the new nodes, so the resource managers can see the added new nodes as long as we run the node managers or the daemons. So we had the data nodes on the 6 nodes, but for those, the new nodes, they are just task nodes. For scale down, we kill the node managers or the slave daemons. And for Yarn, we make sure we configure the number of executors to be sufficient, so that when you add new nodes, they can launch on the new added nodes. So next, I'm going to talk about how does the workloads can actually benefit from the auto-scaling. Here is the runtime comparisons by running those 4 work nodes on the Yarn resource scheduler. So if you can see, the second column is the baseline. They're running the workloads on 6 nodes. So for the third column is the runtime when you do the scale out. So when we run the workloads, we wait for like around 45 seconds. Then we run the 4 new nodes, and you can see that the runtime reduction can achieve up to 46%. But for PageRank, SQL, and logistic regression, they are not actually not that much. Ideally, you want to have the resource improvement by around 40% because you are adding like 40% of the resources that you have in a cluster. So we kind of have identified two reasons why this is happening. One of the reasons is that the delay scheduling capabilities, the resources the task cannot run on the new added nodes very effectively or quickly enough to leverage that because they value the data locality. Once you launch the new node, they don't have the data locality, then they have the tendency to run them on the original nodes. And secondly, is because of so also it depends on the workload characteristics. So for PageRank SQL queries, they are kind of very shuffle intensive. Although you can improve the parallelism, however, you are kind of running on more nodes, you actually increase the network traffic. So there's a trade-off, there's a sweet spot. Some of the applications, they can benefit from the auto scaling, but some of them, because you are increasing the network traffic, and actually it doesn't improve that much. So we also wanted to, so I have mentioned about the two reasons, and then let's dive more detail in terms of how the detailed delay scheduling can prevent the task to be scheduled on the new nodes. So on the last column, right hand side, you can see actually the percentage of the tasks running on the new nodes when you do the scale out. The k-means can achieve around 25%, but ideally you want the number of tasks to be around 40%. That's where the portion of the new nodes in the cluster. And for PageRank SQL queries, they are around like 13% and 12%, and for logistic regression, it doesn't have too much. It's because the delay scheduling, the default value is 3 seconds, and for logistic regression, they have the tendency to run on the original nodes. That's why you don't see actually too many of the tasks running on the new nodes. But for k-means, since the per task runtime, they are longer, and then it seems the tasks, if they can wait for more than 3 seconds, they can be scheduled on the other nodes instead of the nodes that are local. So we also identify, because one of the main reasons is that the new nodes are not very effectively utilized. So we have identified two of the key parameters in Spark to see how can we tune the parameters so that the new nodes can be more utilized more quickly and more efficiently. So one of them is the locality wait time, which controls the delay, which is the key parameter for delay scheduling. So the intuition is that if we can control the locality wait time to be shorter, then it can run the task on the other new nodes more quickly by not respecting the data locality. But on the other hand, you kind of increase the number of you kind of increase the network shuffle traffic, so there's a trade-off. And also, the resource revival interval is another parameter that tells the scheduler how often it tells the scheduler that I have the resource available. So basically, if you set it to, the default value is 1 second. If you set it to smaller number of seconds, then the schedulers can have increase the possibility to leverage the idle resources more frequently. So we want to see how does these two parameters impact the auto scaling and how quickly it can affect the natural new nodes. The top tables, the first column is the second column is the baseline, and the second column is the scale out, which I have shown in the previous slides. And the fourth column is about changing the revival interval from 1 second to 100 milliseconds. You can see actually it doesn't affect that much. But on the other hand, you can see the locality wait time. If we change from the default value from 3 seconds to 100 milliseconds, it actually improves the performance quite a lot compared with the naive scale-out case. It can, in particular, reduce the runtime from 30 minutes of k-means to around 12 minutes. And so for all the cases, it all improves the performance if you reduce the locality wait time. But for the case of if you go to the other extreme by setting the locality wait time to 0 milliseconds, it actually somehow negatively impact the performance because although you can leverage the new nodes faster, but you are kind of increasing the network traffic because you are not respecting the data locality. So the bottom table shows the percentage of how many new nodes are being launched in the case of 100 milliseconds and locality wait time for 0 milliseconds. So you can see by setting the locality wait time to 0 milliseconds, it can actually launch the task around 40%, which is close to the ideal case. So let's quickly look at how the resource utilizations of k-means in terms of the new nodes. So you can see we have shown 6 graphs of the utilizations in terms of scale out of locality of 100 milliseconds versus 0 milliseconds. So what is interesting is the bottom 2 graphs, which shows the scale out case of the new nodes. You can see it actually quite effectively utilizes the CPU resources for the k-means, which is consistent with what we have seen. And for network utilization, the graph here shows that if you do the baseline, you just look at the curve, the area under the curve. So you see for baseline, the curve, the area is small, but for scale out, the 2 scale out cases, the network traffic is kind of similar. But when you do the adding the new nodes, it actually increases the network traffic. For memory utilization, the takeaway from this slide is that when you do the scale, actually the auto-scaling capability can leverage the memories quite effectively on the new nodes. So we also show the page rank, the CPU utilization. What is different is that for scale, when you set the locality to 100 milliseconds, the CPU utilization on the new nodes is not very high because it's not launching a sufficient number of new tasks on this node. But when you set the locality wait time to 0, then you can see the CPU utilizations increase about around 50 to 50%. So which means the tasks are running on these nodes. For network utilizations, so we also see that compared with the baseline, the 2 cases of scale out, they kind of increase the network traffic quite a bit. So for memory utilizations, we also wanted to show the same trend that in terms of the memory utilization, the auto-scaling capabilities can leverage the memories, the newly added memories on the new nodes quite well. So we wanted to show the network traffic utilizations for the SQL queries because when in the previous slides we showed that the SQL queries they had a performance degradation when you set the locality wait time to 0. So one of the reasons is that the network traffic is kind of being increased in this case compared to compared with the scale out case of 100 milliseconds. So the takeaway from this slide is by doing the study of impacts of how the workloads can benefit from the auto-scaling capabilities, we observe there are 2 reasons that prevents the auto-scaling or the workloads to benefit from them. One is the locality wait times because of the scheduling. They want to, when you add a new nodes, the scheduler tend to respect the data locality, and then they tend to run the tasks on the original nodes instead of running them on the new nodes. And so if you can tweak the locality wait time so that they can launch the new task on the new node quickly, and so you can actually leverage the new nodes well better. But you actually somehow negatively increase the network traffic. So there's a trade-off that you have to consider. So the second bullet talks about you are also have to consider although the auto-scaling enables you to increase the parallelism, but you on the other hand, you increase the network traffic, so it depends on what's the workloads that you are running, whether they are shuffle intensive, they are compute intensive. So ideally, the compute intensive workloads can benefit from auto-scaling compared with the workloads that are shuffle intensive or IO intensive. We also did some initial explorations in terms of the scale down case. So in this case, the baselines are running the workloads on 10 nodes compared. Then after like around 3 minutes, we scale down. So you see, actually, for K-means, the runtime is significantly degraded compared with the baseline. But for paging, SQL queries, and logistic regression, they are not too much badly impacted. So you also have to look into the workload characteristics to see whether you want to scale down. So we also observe that when you do the scale down, you can incur lots of task re-execution. So here next we propose some of the ideas or initial thoughts in terms of how can you do this scale down without negatively impact the performance too badly. One of them is kind of you want to actually gracefully gracefully shut down the node executors instead of brutally shut down the executors. Ideally, you want to make sure that the task can finish before you shut down the executors. So one way you can do is that you stop scheduling the new nodes on the nodes that are selected to be removed. Then after all the tasks running on the nodes are removed, then you can shut it down. But another thing in terms of shutting down the nodes is because of you have some intermediate shuffle data or intermediate data stored on the nodes that you want to remove. So how do you do about that? Do you remove the data? But in this case, you can somehow increase the network traffic because you are moving the shuffle data. But those are just some initial thoughts. We haven't done any more experiments or only any in-depth study of that. Next, I'm going to talk about one of the initial optimizations that we do in terms of the auto-scaling. So previous set of experiments, we just wanted to see what's the very basic capabilities of auto-scaling and how workloads can benefit from the auto-scaling. In here, so we kind of looking into some existing auto-scaling mechanisms that Spark current supports and see how can we, what's the limitations, are there any limitations, what's the improvements that we can do. So the dynamic executor allocation is currently supported by Spark, and the basic idea is that it requires a new executors after a fixed time interval. So by default, it's 5 seconds in version 1.3.1. And then when there are some pending tasks, they can detect that and launch the new executors exponentially until it hits the upper bound of the number of tasks. And also, but there are some kind of potential inefficiencies. One of them that we have identified based on the study that I have shown before is because the data locality wait time is kind of 3 seconds. So one of the ideas that we propose is, can we somehow dynamically change the data locality wait time? The intuition behind is we want to, when we detect that the cluster is doing auto scale out, we want to set the locality wait time to be very small, 100 milliseconds or 0, so that the task can quickly launch on the new nodes. When it's stabilized, then we can change the data locality wait time to be the original value, so that it can continue to respect the data locality choice. So this is what I've just discussed, that one of the opportunities is to dynamically allocate or change the data scheduling. So here is like some implementation details in terms of how do we dynamically set this locality wait time. So the basic idea is that we want to make sure that the number of tasks are spread across evenly on the executors. So we kind of periodically monitor. We calculate what's the average number of tasks per executor periodically, since the number of executors can change. So if for the new nodes or for the newly launched executors, if they don't have sufficient enough of the tasks that's running, so it seems it's not, the task is not launching very quickly, then we change the locality wait time to 100 milliseconds or 0 seconds, so that the new task can launch on the new executors faster. Then we turn it back. After we see there's no executors that below some thresholds, it seems like the tasks are kind of spread evenly across all the executors. Then we set back the locality wait time. So here are some of the initial results that we get by doing this dynamically adjust the locality wait time. So the second column is like the scale out with this dynamic executor allocation. So you can see the third column is about the number of tasks on the new nodes. By waiting 3 seconds, it's static, it doesn't change. So the fourth column is that if we implement a dynamic change of the locality wait time, we actually see quite a bit of improvement compared with the DEA algorithm. So particularly for K-means, but we haven't seen very significant performance improvement in terms of the other three workloads. So we also have identified some of the potential auto-scaling performance improvements. So basically, an auto-scaling mechanisms has to answer 3 questions: when to scale, how many more virtual machines, or how many less virtual machines, and whether to scale, does it still beneficial? So existing solutions that kind of decide when to scale by kind of doing, if they observe some of the tasks that are backlogged in the queue, then they will request some more CPU resources, hoping that the increased parallelism can reduce the runtime. But this can work when the workloads are CPU-intensive workloads, but if they are shuffle-intensive workloads or IO-intensive workloads, that might not be very beneficial. So the idea is that you want to look into the workloads characteristics by monitoring the resources utilizations and see what is beneficial. So, but there are some more tests to do. You might have to do some quantifying numbers and quantifying how exactly number of network bandwidth traffics incurring in these workloads will not benefit from this auto-scaling case. So the current existing work in terms of deciding how many more virtual machines to scale, they kind of leverage exponential number of increasingly increase the executors exponentially. This might not be a good way of doing so, because because it goes slowly in the very beginning, but why not just utilize some percentage of the task queue then, so that you can benefit more quickly, because some of the workloads they might run shortly, so you might lose the opportunities by adding slowly. Whether to scale, the current existing solutions, they always scale, but it might not be necessary if it's near end, if the workload is going to finish in maybe in the next 5 minutes or next 1 minute. So maybe some optimizations you can do is like you estimate how many percentage of data is not being processed, and what's the rough estimation of the job execution time left. Then you can decide not to scale if your job is finished quickly. So I have talked about the studies of the workloads, how the workload benefits from the scaling, and what's the factors that impacts the auto-scaling capabilities, and initial optimizations that we do by dynamically changing the locality wait time. Next, I'm going to conclude with some of the lessons and future work. So it turns out that the basic auto-scaling can help, but it depends on the workloads and so there are 2 trade-offs, and also the delay scheduling might not be very effective of leveraging those new nodes quickly enough. We also try to dynamically changing the locality wait time, and it can be effective in terms of making use of the new nodes in a fast way. Basically, another reason is that you have to identify what's the network traffic, what's the workload characteristics. If it's traffic intensive or IO intensive, maybe it will be less effective in terms of leveraging the new added compute resources. So in the future, we plan to study the scaling effects on multiple workloads, and also we want to somehow enhance the dynamic allocation mechanisms to leverage to estimate the job run times, and that's it. Thank you for your attention.
Okay, are there any questions? Can you come up to the microphone, please?
So a lot of the possible improvements that you lined out are generally around scheduling and things like that. And that reminds me somewhat of a similar problem, which is scheduling on plain old hardware. Something that has been well understood by now when it comes to operating systems, and partially solved at least using proactive scheduling and anticipation of future workloads. Is that an avenue that you think is realistic for Spark? Predicting the future workloads and auto-scaling and shuffling based on this, rather than waiting for workloads to actually demand those changes.
Could you repeat your question again?
So the general idea around scheduling is, what you lined out around scheduling is that most loads wait when they see that there is a lack of resources to create new nodes, and eventually have to pay a high cost in terms of shuffling the data and pushing RDDs locally. One solution to this would be to anticipate future needs and react to predicted future load by proactively creating new nodes and shuffling data to those new nodes, so that when the application actually needs those resources, the nodes are already up and running and ready, and the data is cached.
Yes, I think this is a good optimization. Yes, you can anticipate and proactively push the data to the new nodes so that it can benefit for those shuffle-intensive workloads. Yes, I agree. Yeah, but there are lots of works that you have to do. So here we kind of saying that if you don't do those, and current frameworks will have to suffer from this case. Yes.
Okay, let's thank